So Troy will tell us about Grothendieck and more.
Okay, thanks.
Oh, that's nice.
Okay.
That's the thing we shouldn't touch.
Okay, so this is joint work with Joop Briet, Harry Berman, and Thomas Vidic. Okay, so there's a lot going on in the title. So first, I'll just explain the words in the title in the two-party case and the relationship between them. But my eventual goal is to port all this into the multi-party case. So I'll talk about the three-party case and talk about what of the relationship between these things survives. And the final goal and result will be, partial result towards that goal will be to show that the discrepancy method and also this generalized discrepancy method lower bounds three-party quantum communication complexity also with limited forms of entanglement. Okay, so that's sort of the roadmap. So let me start out just with the XOR games. So this is a very simple model of computing a function of two arguments f. Okay, so the verifier chooses two in-bit strings, x and y, with probability pi of x comma y, and sends x to Alice and y to Bob. Okay, and now Alice and Bob can't communicate with each other. They each just select a bit, plus or minus 1. And their goal is that the product of these bits is equal to the function value. Okay? So just given their input x, say given Alice's input x, she chooses some bit ax, and same thing for Bob. And their goal is that the product of these is equal to the function value. Now, of course, if the matrix described by the function is not rank 1, then you're not going to always succeed, right? Because their protocol basically just will define a rank 1 sign matrix. Okay, so the measure that we're going to use for how well they do is the bias. Okay, so this is just the probability under pi that they get the right answer minus the probability that they get the wrong answer. Okay, and so since f is plus minus 1 valued, it's expressed nicely in this form.
You're going to mention why it's called XOR games?
Why it's XOR games? Oh, well, okay, so here, I mean, I'm using plus minus 1 valued things, but I mean, say if you're talking about 0, 1 valued things, then you want the XOR of their answers to be the function value.
So the initial function for which this was done was the end function of 2 bits.
Right, yeah.
That has to do with the EPR.
Right, I'll get to that, yeah.
Right, sorry.
Yeah. Okay, all right. All right, so let me just make a couple of basic comments about this model. So as I described it, it's totally deterministic, right? Given x, Alice just chooses a bit. Right? I mean, you could also consider the model where Alice and Bob, say, share a random string and use this to as part of their strategy. But you can show by a convexity argument that this actually doesn't help them. Okay, so they can't increase the bias by doing this. So this really doesn't affect the model. But at times it is convenient to assume that they share randomness. So at times I will do that if it helps me. The second comment is just to relate the bias of a game to, so it's actually described by a norm called the infinity to 1 norm. Okay, so so the bias, remember, was just given by the sum of AXY times some bit AX times BY. So this is just another way to express that, right, as this quadratic form. So basically this vector X, this describes Alice's strategy, okay? And the same thing with this vector Y describes Bob's strategy.
So these were the names of their inputs.
Yeah, you're right. This is bad notation, I guess. Yeah. Right, yeah. So really, right, this should be a vector A, I guess, and this would be a vector B, say, where the xth entry of A is plus or minus 1. Okay?
And capital A is a function matrix.
That's right, yeah. Right, if you just expand out this quadratic form, you get exactly what we had on the previous slide, where now A is like the matrix where the xy entry is pi of xy times f of xy. Okay, so now the reason why this is called the infinity to 1 norm is that, say I take the maximum over y here, well, it doesn't change if I just take the maximum over strings where every position has magnitude at most 1 instead of just signs, okay? And the idea is that once Bob actually chooses his strategy, then the best strategy of Alice is fixed. So namely, once Bob chooses his strategy, then we look at this vector A times Y, and the best thing that Bob can do is just to choose every plus or minus 1 to make each entry of A times Y positive. Okay?
Isn't that the same as the one-way communication, the same measure that captures one-way probabilistic communication complexity? Infinity to 1?
No, I wouldn't think so. I mean, one way is just like the number of rows, distinct rows in the matrix. Probabilistic. Yeah. Okay. Yeah. Okay, so that's why it's called the infinity to 1 norm. You take the max over things with L infinity norm at most 1, and you take the L1 norm of the result. Okay, so we're also going to be talking about XOR games with entanglement. Okay, so this is interesting because the XOR model is a very simple model, and you can already see the impact that entanglement can have as a resource in this model. And furthermore, you can actually sort of simulate these XOR games with entanglement in the lab and do experiments and actually see the effect of entanglement. Okay, so in this model, Alice has some Hilbert space HA and Bob has some Hilbert space HB, and they share a bipartite state, okay, in the tensor product of these spaces. And now, instead of choosing bits, so now, instead of choosing bits, you're going to choose Hermitian matrices, capital AX and capital BY, that have plus minus 1 eigenvalues. Okay? So these are really just Hermitian unitary matrices. And now, on input XY, the expected value of the output, instead of just being the bit AX times the bit AY, it's going to be this quadratic form, okay? All right? So now the bias will be given by this expression. You maximize over their strategies, so choices of these Hermitian unitary matrices, and you take the sum over all possible inputs of the correlation of their output with the input. Yeah.
Maybe you could explain it in more intuitive terms what's going on. So what are these matrices AX and BY? Are they measurements that
Yeah,
the two parties do?
right. It's just like Alice is making a measurement on her part of the state and Bob.
So does it matter? Now, this looks symmetrical.
Yeah.
But my intuition might think that it might matter who measures first.
Right. No, because I think, Alice's, she just acts as the identity always on Bob's part. And Bob
But
acts
if they're
so these things
entangled-
commute.
Phi could be entangled. So is that actually okay? So it's not okay.
That's a tricky consequence of non-signaling. Whatever Alice Bob, it cannot change whatever Bob does. So it doesn't change whether one measures first or the other. It's just a consequence of relativity.
This matrices AX times the terms of the identity and identity terms of Vy are commute.
Yes.
Yeah.
It's a mathematical way of saying.
Right.
But okay. And say what if you have an EPR pair?
Yeah, that's yeah.
So then whenever you measure, that's gonna. Oh, I see.
Right.
So it doesn't matter
But they
if
commute,
But
yeah.
it's just implicit commute.
Okay.
Yeah. Okay.
If you look at the bit that is APR pair and you see what it is, or it's fixed on the other side, whatever Alice measures it.
Right.
Will be
Right.
that bit.
Okay. So that's the definition of the bias with respect to some particular state psi, and then overall the bias is just the maximum over the possible entanglement that they could share. Okay? And so I just used beta for the classical bias, and now I have beta star for the bias
So
with
the
entanglement.
game is that they are allowed to consult in advance how
Sure.
they both choose the best entanglement.
Exactly.
Which is a strategy
Right,
for them to
exactly.
play the game,
Yes,
and then
yes.
the verifier
That's right.
gives them.
That's right. Yes?
I'm sorry, I don't think I understand what the objective here.
Well,
Like, how do you interpret this objective?
They are trying to maximize the probability that they compute the function in this.
but when replacing ax dy by this inner product.
Can I think of this inner product as
Yeah.
sort of both produce a number which is maybe between 1 and -1, and they sort of output 1 and -1 with the right probability, and this is just sort of the product of the probabilities.
Well, that would just be a classical strategy, right? If they just...
No, but if they first perform
Yeah.
a Hermitian operator on their
Yeah,
part of
yeah,
the
yeah.
shared quantum state,
Right.
then apply a measurement, and
Right.
then it either collapses to 1 or -1, say.
Yeah.
And so this is the sort of expected product.
Right, okay, yeah, okay, yeah, yeah. Sure.
So phi here's the psi
Yeah.
is not the input. So is pi xy classical? So it's just
Yeah, this is just a probability
it's
distribution.
not-
Yeah.
it's
Yeah.
not
Yeah, yeah.
entangled state.
No.
Okay.
Yeah.
So and then psi is sort of like the best kind
Right.
of public randomness they could have, or
Okay, the analogy of public randomness,
So,
I mean,
but it
this is
doesn't
entanglement.
have any correlation. It's independent of that x and y.
Yeah.
Yes, yeah.
So it's like
Their
a
joint
giant sort of-
strategy.
Right.
Their joint strategies encoded
I
in
see.
psi.
So the entanglement happens before they get their.
That's right, yeah. That's
Okay.
a parameter of the game. Yeah. Okay, so maybe it'll be more clear what you can do with entanglement from this slide. Okay, so Cyrilson gave a very nice characterization of XOR games with entanglement, which is a lot easier to think about. Okay, so what he showed is that the maximum bias you can achieve is just the maximum over unit vectors, ux and vy. So now for each input x, Alice chooses a unit vector ux of the sum over x and y, probability that they get x and y, f of x, y, times the inner product of these unit vectors. Okay? So now...
Semi-definite relaxation of the...
That's exactly right, yeah. So now you see how they can improve, right? Before, they could just choose a scalar. Now they can choose unit vectors, okay? Okay, so, and actually the fact that this is an upper bound on the bias is easy to see. So we can create unit vectors whose inner product is equal to this just by taking ux to be ax tensor identity on psi. And since ax is a unitary, this whole ax tensor identity will also be unitary. So this will just be some unit vector, and the same here. Okay? So the other direction is no, it's actually it's a construction. I mean, given these vectors, then you actually construct these. The other direction is quite nice. Yeah. Okay, so let me give an example. So this is what Avi mentioned on the first slide. So this is what physicists call the CHSH game, but mathematically you can just think about it as the 2x2 Hadamard matrix. Okay, so Alice and Bob each both just get a bit, and their goal is that, and they want to output ax and by, and their goal is that this product is equal to the AND of the bits that they receive. Okay? So the game matrix is just a Hadamard matrix. So if you think about 1 as false and -1 as true, and this corresponds to the, I labeled the rows by 1 and -1, okay? And I just put the uniform distribution on this, okay? So I just get a quarter out front. So now classically, so as I mentioned, you can only do perfectly classically if your matrix is rank 1. So since this matrix is rank 2, they must make a mistake somewhere, at least one mistake. And in fact, they can just make one mistake if they just always output 1, okay? So that gives bias 1 plus 2 plus 3 minus 1, so 2 over 4, or a half. Okay? And now you can see how with entanglement you can do better. Okay? So you can actually achieve bias root 2 over 2. And I'm going to be using Cyrilson's characterization here. So I just want to, design unit vectors ux and vy to do better. Okay, so I'll show something more general. So so think about the trace norm of A. Right? Okay, so this is just the sum of the singular values of A. And you can write this as the maximum over unitaries u and v of the trace of ua v star. Okay, so you can just think of the rows of u as being like the left singular vectors of A, and similarly with the rows of V. All right? So if I just rewrite this, so since the trace is cyclic, I can just bring this U over to the other side, and then I write it in sort of vector form. So this is just max over orthonormal sets of unit vectors, Ux and Vy, the sum of AXY times the inner product of Vy and Ux. Okay? So Ux is just the rows now of U, and the same with Y. Okay, but you see that this is, that the classical, the bias with entanglement by Cyrilson is just a relaxation of this, okay? Because we don't have to take the vectors to be orthonormal, we just have to take them to be unit vectors, all right? So the bias with entanglement is always going to be larger than the trace norm, all right? So the trace norm for the 2x2 Hadamard matrix is just, singular values are all root 2, so it's just 2 times root 2. Then I normalize under the uniform distribution, I divide by 4, so the bias is root 2 over 2. Okay?
And this is again that proves that there is no classical
Right.
realization of
Yeah.
quantum mechanics.
Right. In physics terms, right, you interpret the classical bias as like hidden as local variable theories. And I guess they've actually, implemented this in the lab. So. Okay, so we've seen that you can do better by this factor of root 2 if you share entanglement. So you might ask, how much better can you do in general? Okay, how large can this gap between the bias with and without entanglement be? And actually, root 2 is pretty close to the maximum. Okay, and this is where Grothendieck's inequality enters in. So Grothendieck's inequality in other terms, it exactly relates the bias with entanglement to without entanglement. So what it says is that this correlation with inner product of unit vectors is bounded by a constant times this infinity to 1 norm. Okay? And this constant is in fact quite small. So, right, so, and as Avi said, I mean, you can also think about this in computational terms. I mean, this infinity to 1 norm is actually NP hard to compute. It's like a, integer programming problem, whereas here, this you can compute by semi-definite relaxation. And this, is telling you about the integrality gap of this semi-definite relaxation. And Alon and Noor actually showed how you can round the solution to the semi-definite program to actually approximate the infinity to 1 norm.
The infinity to 1 is max cut, the cut norm.
It's up to constant factors, yes. Yes. Right. That's right. That's exactly right. Yeah. Okay, so it's also interesting that this 2 by 2 matrix already gives such a large gap. And there's another paper by Reeds, so one of the guys who showed this lower bound, and Fishburne, who are basically looking for small matrices with large gaps. And the smallest matrix that they can find with a gap larger than square root 2 is like a 20 by 20 matrix. So it's sort of interesting to find small matrices with large gaps. Okay, so now let me talk about the third thing in the title, communication complexity. And the connection with XOR games is the following. If you can show an upper bound on the bias of f in an XOR game with respect to any distribution you like, then you can get lower bounds on the communication complexity of f. Okay, and the way that this works is fairly simple. So say that f has deterministic communication complexity c. Then what we're going to do is we're going to use this protocol, this communication protocol, to design a strategy in the XOR game where the players achieve bias at least 2 to the minus c. And this is going to be independent of the distribution, so it works for any distribution. Okay, so as I said, we can freely assume that the players have access to shared randomness. So basically what they're going to do is they're going to share a random string of length c and interpret it as the transcript of their communication protocol. Okay? So, and basically what they're going to do is they're just going to go through their communication protocol only without communicating. So Alice looks at her input and she says, okay, on this input, I'm going to send the bit 1. And then she checks if actually the first bit of the shared random string is 1. Okay? And then Bob, so if it is, then everything is okay. And we say that the random string is consistent with the protocol. If it's not, then it's inconsistent. So Bob does the same thing. He looks at his input, and he looks at the first bit of the random string, and he assumes that Alice sent him that bit. And then he says, okay, under those conditions, I will send the bit B2. And then he checks if B2 is equal to the second bit of the shared random string. Okay? Again, if it's not, then we say that the random string is inconsistent. Otherwise, it's consistent. Okay, so they keep going in this way. And if either player notices an inconsistency, they just output a random bit. Okay? And otherwise, if Alice goes through the whole protocol and doesn't see any inconsistencies, then she just outputs the function value. Right? The function value is determined by the transcript. We can just assume it's the last bit of the transcript. And if Bob doesn't notice any inconsistency, then he just outputs 1. Okay? So let P of xy be the expectation of the output of this protocol. Okay, so, and let's look at the correlation that this protocol has with f under the distribution pi. So, if the random string is not actually their transcript, then the expectation of p of xy is just 0, because then either Alice or Bob will at some point notice an inconsistency and will just be outputting a random bit. Otherwise, if the string is correct, which happens with probability 1 over 2 to the c, then they're just going to be outputting f of xy, because we assumed a perfect deterministic protocol. Okay, so this achieves bias 1 over 2 to the c. Okay. Okay, so you can extend this idea to also work with bounded error protocols. So, so if we have a bounded error protocol, this, if you look at the expected output of the communication protocol, then if the answer is 1, your output, the expectation of the output will be somewhere between 1 minus 2 epsilon and 1, right? Because then with probability at most epsilon, you output minus 1. Probability at least 1 minus epsilon, you output 1. Okay, and similarly for in the case that the answer is minus 1. Okay, so if we just plug that into what we had in the last slide, now with probability 1 over 2 to the c, instead of getting f of xy exactly, we'll just get at least 1 minus 2 epsilon times f of xy. Okay, so we're going to get correlation at least 1 minus 2 epsilon over 2 to the c. Okay? Yeah?
The fact that you get that Bob always sends 1,
Yeah.
can this quantity be either a real difference,
Yeah.
it gives a different kind of more restricted quantity.
Yeah.
So could there be a real difference between the two numbers?
I don't think so. I mean, you know, it depends exactly how you define things. But anyway, I think these definitions will only change things a small amount. So, you know, the way that you normally define a deterministic communication protocol is that at the end both players know the answer. Right, so it sort of doesn't matter that that I've done it asymmetrically here. I mean, right, you could also, you know, consider the, you know, define the communication complexity where, you know, where again you take the XOR of,
So instead of taking the sort of infinity to 1 over
yeah,
one of the vectors is like the one vector.
I mean, it doesn't always send 1, right? Because it sends random.
right, yeah. I mean, just sort of say, yeah, I don't think it looks a bit asymmetric, but yeah, I don't think you lose anything.
You can only change the communication complexity by 1 bit. Whether you change it.
Right, yeah, I guess, yeah. Okay, so what I've shown now is that the bias is at least 1 minus 2 epsilon over 2 to the c if f has communication complexity, randomized communication complexity c. So if you rearrange this, it basically means that the randomized communication complexity of f is at least log 1 minus 2 epsilon over the classical bias of f under the distribution pi. Okay? And the distribution pi didn't enter in anywhere here, so I can take the max over all distributions. All right.
Does it ever give better bounds than discrepancy with this method?
I wish there was the next slide.
Well,
It's like in 2 slides. Okay. Okay, so so this connection of showing upper bounds on bias and turning that into lower bounds on communication complexity, I mean, it's quite general. I mean, you see that I used very few facts about what kind of protocols you have. So it also works for protocols with entanglement. So, I mean, the proof is sort of exactly the same. The players just do exactly what they would do in the communication protocol and are checking if what they would send agrees with this shared random string. So here I'm talking about protocols with entanglement, but where they still send classical bits. So they still interpret this shared random string as the transcript of the communication. And as we discussed earlier, I mean, it doesn't matter what order players do things. So they can just, they're doing this independently, and that's fine. So the same argument gives that the randomized communication complexity with entanglement can be lower bounded by this quantity, where now I have the XOR bias with entanglement. Okay? But because of Grothendieck's inequality, I know that this is at most a factor of 2 larger than just the classical bias. So even showing upper bounds on the classical bias will give me lower bounds on randomized communication complexity with entanglement. Okay, so now I just leverage this one step further. So I can also get lower bounds on protocols that have entanglement and also send quantum communication. And the reason for this is that basically protocols with entanglement and protocols with quantum communication and entanglement are essentially equivalent. So entanglement already allows you to simulate sending quantum messages. Okay, so in fact you just lose a factor of 2. And the idea here is this teleportation. So if Alice and Bob share a state of this form, which is called a Bell state, and Alice wants to send Bob a message alpha 0 plus beta 1, she can do this by just doing local operations, local unitaries on her side, and then sending Bob 2 classical bits of information which basically direct him to do specified local operations on his side. And at the end of this process, he'll have this state sitting in his register. Okay? So with just 2 bits of classical communication and shared entanglement, you can simulate sending quantum messages. Okay, so what I've outlined here, showing lower bounds on communication complexity by showing upper bounds on XOR bias, this is really just the discrepancy method in a different language. Okay, so as Avi said, the discrepancy, it's essentially the same as the infinity to 1 norm. The only thing is that instead of taking the max over plus minus 1 vectors, you take it over 0, 1 vectors. Okay? So, so the discrepancy is exactly just the cut norm of your game matrix integrized product with a probability distribution. That's the discrepancy with respect to that probability distribution. And these, it doesn't make that big of a difference if you maximize with respect to 0, 1 vectors or plus minus 1 vectors. Okay. Okay, so so what I've outlined so far is sort of the normal discrepancy method, but you can actually use these ideas to obtain even stronger lower bounds, which is what's called the generalized discrepancy method. So this is an argument that goes back to Clark and Razborov. And the idea is that instead of showing upper bounds on the bias of the function that you're interested in, f, you instead just show upper bounds on the bias of, you can instead show upper bounds on the bias of some other function, g. The idea being that f itself could have large discrepancy, but it might be correlated with some other function g, which actually has small discrepancy. Okay. So the proof of this is very similar to what I said before. So if f has small communication complexity, then I have an XOR protocol which achieves large bias on f. But if f also correlates with g under pi, then I can just use the strategy for f when I'm playing the game for g. And this will still give me reasonable correlation. In fact, the correlation will just be like the correlation of f and g under pi. Okay? Right. So basically, I can get a lower bound of the form. I can maximize over functions g and pi. And as long as this correlation is non-negligible, I can still get a lower bound of like 1 over the bias of g under pi. Okay?
So stop lower bound for disjointness works exactly this way.
That's right. That's right.
So,
Yeah.
so this is not equivalent to just showing that f itself has a small bias?
No, it's not.
No, it's not. Yeah. Yeah.
Disjointness, for example, has loudly discrepancy. I mean, that's big discrepancy.
No, but if you are free to choose pi,
No, even if
Yeah.
you don't get anything
Yeah.
if you apply the discrepancy with any distribution to the disjointness makes it. But if you correlate it, if you do this trick, apparently you gain a lot. Yeah. So
Yeah.
there was a, or you're
So
going
you don't
to,
get a
you're
bias
going
even
to
though-
tell the disjointness story.
No, not so much. No.
So there was a quantum complexity of disjointness was not known for a while whether it's polylogarithmic or polynomial, and that was both of the lower bound, something like cube root of n, but using a pretty complicated method, and then Sherstow found the method just along this line, just a discrepancy, but the function correlated with discrepancy.
so
To get a type of
so f itself could have a very large bias under pi,
yes.
Under any pi, right?
under any pi,
Yeah.
but
Some function that correlates with it has a very tiny
This is like allowing sort of negative probabilities in your distribution pi, right? Because you're
That's exactly right. Yeah.
so instead of multiplying with
yeah.
pi, you're multiplying with g.
That's right. Yeah, that's a nice way of looking at it. Right, because before I was just maximizing over sort of non-negative distributions, and now, I mean, you can alternatively think I'm maximizing over g and pi, and I take the inner product with this integral product. So really, I'm just maximizing over an arbitrary matrix which has entries, which has L1 norm 1. Okay.
and then you don't need to talk about g. You just
That's right. Yeah, and thinking about it that way is quite pretty, because then this expression. So if you just ignore this minus 2 epsilon for a minute, then this expression maximum over let's say B, just some matrix with L1 norm 1 of the inner product of f and b over the infinity to 1 norm of b. This is exactly the dual norm to the infinity to 1 norm. Okay, so the definition of a dual norm, you just maximize over b the inner product of f and b divided by the norm of b. Okay, and this is actually the way that Linneo and Schreibman look at this. Okay, and they
Sherstow did it after Linneo Schreibman.
right, I guess, yeah. Okay. And I also really like that point of view, but which is how I've normally thought about it. But now I've sort of been convinced that this dual view is perhaps maybe a bit simpler. I mean, you can see that I've essentially proved this statement to you, right? Because for this, you only needed the easy direction of Cyrilson, which is quite simple. So, I think this might be the fastest route to get this, to get this lower bound. But the dual view, I mean, is certainly is very nice and complements this view. Yeah. Okay, so as we discussed, it is quite surprising that this this doesn't seem like a method that will be very good, right? I mean, you're showing lower bounds on communication complexity just by talking about these XOR games which have no communication at all. And okay, you do this trick where you can, you don't talk about the bias of the function you're interested in, but some other function that correlates it. But, it's not, a priori, you might not think that helps you too much. And okay, so it is true that, this sort of method, this generalized discrepancy, it is a lower bound on quantum communication complexity. So for disjointness, there is a quantum protocol with complexity square root of n. So you're not going to do better than that, whereas the randomized complexity is, n. So here, this sort of information theoretic techniques and like the corruption bound, can show a tight bound on disjointness. So they do better than this generalized discrepancy method. But on the other hand, this technique, it does subsume a large class of you might call them geometric techniques. So Lineal and Schreibman showed that it's larger than this trace norm method that Razborov originally used for the root n lower bound on disjointness, and some other Fourier analysis-based technique of Raz, and some techniques based on other matrix norms. They show that it subsumes all of these techniques. And in fact, it turns out to be polynomially related to approximate rank. So approximate rank is you have your game matrix given by F, and you look for the smallest rank of a matrix which is entry-wise close to that matrix. Okay, so it just differs by epsilon at most in every entry. And you can show that the log of this approximate rank is a lower bound on randomized and quantum communication complexity. And yeah. I think it's quite natural. In my view, it's probably even more believable than the log rank conjecture that this log approximate rank.
Yeah, it's not in your view, it's just easier.
No, I don't think there's a strict implication.
But maybe it depends
Yeah.
on the definition down
Yeah,
there.
right. But yeah, I think it's quite a natural conjecture. Yeah, and so this generalized discrepancy is polynomially related to this approximate rank. So it's actually, quite a strong technique, I think. Okay, so before I move to the multiparty case, let me just summarize what hopefully I've communicated so far. So we want to show communication complexity lower bounds, and we've seen how you can do that by showing upper bounds on the bias in XOR games. And Grothendieck's inequality basically tells you that you don't have to worry about the bias with entanglement. You can just focus on the bias, the classical bias, because these are related by a constant factor. So this means that the classical bias, or the discrepancy, can be used to lower bound even this sort of more powerful model of quantum communication complexity with entanglement. Okay, so now I want to try to port all these things to the multiparty case. All right, so first of all, let me just take care of one small issue, which is, in the multiparty case, there's different ways of distributing the input to the players. So you have what's called the number in hand model and the number on the forehead model. So in the number in hand model, each player, okay, so let's just talk about the three-party case. So now you have a function of 3 arguments, x, y, and z, and the number in the hand model, so Alice just gets x, Bob gets y, Charlie gets z. And the number on the forehead model, each player sees every input except their own, which is you can think of as written on their forehead, right? So Alice gets Y and Z, Bob gets X and Z, Charlie gets X and Y, okay? But for us, actually, this distinction doesn't matter so much. So we're just going to think about a number on the forehead problem as a sort of a promise number in the hand problem, okay? So, so I just transformed the number on the forehead problem to a number in the hand problem by giving each player all the inputs that they see. And I'm just going to give 0 probability to any triplets which aren't consistent, okay? So which don't form a valid number on the forehead input. And now if I consider bias under such a probability distribution for this transform problem, it corresponds to the normal notion of discrepancy in the number on the forehead case.
But
Okay.
the communication game is defined in the same way. Each of them sends a bit,
Yeah.
and they are exclusive all the bits. It will be
That's
exclusive.
right. That's right. That's right. Yeah. That's right. Okay. So so when I do this, right, I sort of blow up the communication tensor, right? So before, if I imagined the tensor where the sides were just labeled by inputs to each of the players, now I'm going to give them tuples, so I sort of blow up the size of this tensor. But the point is that the things that I'm going to use, like Grothendieck's inequality, they're independent of the tensor. They hold for all tensors. So this blowing up doesn't affect anything.
Well, what effect is? I'm not sure that it's a useful view. For me, it's very hard to think of number
Right.
on the forehand as a number
Right.
in hand. I guess that's what you advocated.
That's right.
So
Yeah.
the problem is not the size of the tensor. It's just that lots of entries are not allowed.
Yeah, that's right. That's right. I mean, the only reason I need this is from the point of view of the Grothendieck inequality, because it's normally defined in a number in a hand sort of way.
Yeah.
And so I just want to apply it in a black box. Right, you can, right. Okay, so first let's see what carries over to the three-party case. So the classical bias, it still corresponds to the discrepancy method. So, right, and the game is again, each player just outputs a single bit and you take the product of all those bits and see how that correlates with the function. And
Is there like some kind of loss, like this kind of 2 to the D loss with the number of players, or this is exactly the same?
He's not going to do just so far, no.
Yeah.
Generalize the cylinder intersections. So no.
right.
So,
Yeah.
so bias is like discrepancy exactly. It's not.
Right. I mean, from now on, just think about number in the hand, say. Yeah. Right.
It's a number in hand model with weird distribution on example.
Even
Yeah.
with some.
Yeah. Oh, I see what you mean. Right. No, this just corresponds to discrepancy, right? I mean, how you bound discrepancy, right? You will still probably eventually lose this 2 to the k. Yeah.
But not at this point.
Not at this point, right? Okay. And also, this relationship I mentioned, so showing upper bounds on the XOR bias, it still implies lower bounds on the communication complexity. Okay, this argument of how to turn a communication protocol into a strategy in XOR game, that's also goes through. What becomes much more difficult is showing upper bounds on the bias with entanglement. Yes?
Can you define what is the objective of the quantum protocol like? The one with entanglement?
Right. Yes, so let's see, I guess I probably don't have that on the next slide. So, right, so
What's upper bounds of bias without entanglement so much?
yeah, that's true, yeah. Okay, so I guess I should say max.
On the right.
So it's exactly the analogous thing. Now, so again, they each choose a Hermitian unitary, depending on their input, and now you just have this quadratic form with the tensor product of all three of them. Okay. This is
There are 3 players.
yeah,
X, Y, and Z.
yeah.
But the psi is like it's entangled over everything.
Over right now, psi lives.
No, but why do they get X, Y, and Z? I thought they should get X, Y, Y, Z, and...
No, because he's speaking
Ah, so
number
you're
in the hand.
already, you're thinking a number in the hand.
Yeah. Right, and right, again, in the classical case, this would be replaced just by AX, B1, three bits. Okay. Okay, so what's known in the three-party case? So much less is known, and you don't have sort of the nice relationships that you have in the two-party case. So there's actually an example given by Perez-Garcia and others where there's an unbounded gap between what you can achieve with entanglement and without. Okay, but they also show that for a special kind of state, which has been well studied, called a GHZ state, there's at most a constant gap. So here you sort of have a...
The special state is psi.
Exactly, yeah.
What?
But
Yeah.
they can choose it any way they like, right? The players.
That's right.
What is
Yeah.
GHZ?
It will come. Okay, so, right, so here you have sort of a very different situation. So we want to somehow classify what kind of states, can give you this unbounded advantage and what cannot.
So here, the kind of vector characterization that you gave before is not clear, right?
Yeah, that's exactly right, yeah. So that's sort of the first problem, is that we no longer have this vector characterization. And also, we want to again try to apply some generalization of Grothendieck inequalities, but to the multiparty, setting, but these things don't always hold. Okay, so
But by unbounded, by the way, it's
Yeah.
like is the notion of exactly how much unbounded? I mean, when you translate over to communication complexity, then you can allow yourself some unbounded factors, no?
yeah, it's really like they show like a square root of n gap. Yeah, so it's yeah. Okay. Right. So I guess I should speed up. So basically, what we do is we reprove this special case of this GHZ state, which I'll talk about in a minute, and we can enlarge the class of states for which you can show a constant gap. And then we show how another generalization of Grothendieck's inequality sort of lets you combine these things, so you can allow various subsets of players to be sharing entanglement. So in particular, we can sort of let every pair of players be sharing Bell states, and this allows them to do the teleportation. So we can actually show that, say, when the subsets of players are sharing GHZ states, we can still get a lower bound on the quantum communication complexity with that kind of entanglement. Okay? And so previously it was known that this general discrepancy method could show a lower bound on quantum communication, but and this was shown from that dual point of view, which I mentioned before, and this didn't seem to be able to handle the case of entanglement. Okay, So what's nice about this is that you're basically, showing that old lower bounds hold in stronger models. So now that we know that the generalized discrepancy method works for quantum communication complexity with these kinds of entanglement, we can immediately transfer, all the old lower bounds to this new model. And that's nice in the number on the forehead case, because there, this generalized discrepancy method is essentially the only method we have. Okay.
So when you say you generalize it, so it's kind of different.
Yeah.
This non-lower bounds now hold also if every pair of players have
Right. Exactly.
whatever entangled state they want.
Well, not whatever they want. Yeah.
Not whatever they want.
No, we can't
Just
handle
every
everything.
pair has
Yeah, have like this GHZ state, for
So that
example.
is at least we can
EPR
communicate
pair
it.
is
Yeah, EPR pair, that's fine.
is allowed.
Yeah, EPR pair is fine, yeah. No, we still can't handle any kind of
Particularly,
entanglement.
it gives you like a unified way to get on quantum communication.
That's right, yeah, that's right, yeah. Right, which might, is maybe already interesting if you're not interested in quantum, because it tells you that this generalized discrepancy method isn't going to show a lower bound better than root n for three-party disjointness. So if you want to improve or show better lower bounds for three-party disjointness, you're going to have to come up with some new method. Okay. So luckily, the sort of most naive extension to Grothendieck that you might want does in fact hold. So if you define this generalized inner product of three vectors u, v, and w, just to be the sum over I of ui times vi times wi, then the analogous statement to Grothendieck does hold. Okay? So this constant, you can choose it to be something like 10, but more interestingly, in the k-party version, this constant. Now look at the sum that I have in the inner part. So this is just a sum from j equals 1 to d of the product of these entries. So notice that as we run over g, we're just taking the generalized inner product of the ith row of A with the ith row of B with the ith row of C. Okay? So what I have here is I just have a convex combination of the correlation of M with the generalized inner product. Okay, so that's going to be bounded by the maximum choice of unit vectors. Right? Since these are unitaries, this row is just a unit vector. Okay, so that's sort of the flavor of our arguments. You want to bound the correlation with entanglement by some function for which you have a Grothendieck inequality. Right. Okay, so so you can extend this argument to more general kinds of states, so sort of weighted GHZ states. They don't have to be uniform. But since I'm running out of time, let me just... Okay, and finally, there's also this Karna's theorem, which is, roughly speaking, sort of a way that you can compose different Grothendieck inequalities. So if you have some functionals which a Grothendieck inequality holds, then you can sort of look at their tensor product, and you'll also get a Grothendieck inequality. So this is how we allow all pairs of players to share Bell states, for example.
I see. So the previous theorem was a triple of
Yeah,
pairs
yeah.
shared a single.
Right.
A bunch of
That's right. That's right.
pairs, but
Exactly. Yeah.
for all three.
Right. Okay. So let me just finish there. So right. I think it's sort of interesting that we know that there's this large gap in the XOR case and the multiparty XOR case with entanglement and when without. And so can you sort of transform this into a communication problem where you also have a large gap? So in the two-party case, we think that entanglement doesn't really help you that much. But that might not be the case in the multi-party case. Okay, thank you.
Questions?
Yeah.
No, I'm not sure that I mean, you transform
Yeah.
this number in on the forehead to number in hand
Right.
model.
Right.
And you change x, y, y, z, and
That's right.
z into x, y, and z.
Yeah.
When you
Yeah.
wrote that a player has
Yeah.
strategy A of x1, was
Right.
this x1 really a pair xy, or was it what was it?
Okay, so what I wanted to do was first state this this general way to transform a number on the forehead to something that looks like number in the hand, and then after that just talk about the number in the hand. But right, if you wanted to pull out this transformation, then A of x1 would really be right.
You prove the BNS law about
Right. Yeah.
So
Yeah.
that's
Yeah.
what you do. You just
Yeah. That's right. Yeah.
So it works in a way that the strategies of the players depend actually on everything they
Right.
see on the foreheads of other people.
Right.
But then these things are not disjoint. It's not like where you say HA,
Yeah.
HB, and HC. They are not really. They are
Well, each player.
it's not like tensor with identity.
No, I think each player does still have just has their own
My measurement
register.
depends. Say we are the three of us are playing.
Yeah,
so
yeah.
my measurement of
Yeah.
the state side
Right.
depends on what I see on yours and Valentin's forehead. And then the
Ah.
blue measure depends on what you see. So it's not like I don't see why these operators commute, for example.
No,
They
but
should,
Avi,
they
you,
don't.
no, but you
only
can only
apply to
measure
your
what
part
you're
of
holding. You can only measure the quantum, the part of the entangled vector that you're holding. The part of that entangled vector is always the same.
Okay, so you
You
don't
don't apply
so-
What kind of operation you'll apply to it, that differs.
Okay, fine. Okay.
Okay, I mean, it's important that the x, y, and z are classical, or else you couldn't really do this. It would be like, you'd have to duplicate the. So, if the x, y, and z were, if the inputs were themselves entangled, then you couldn't do this transformation because having access to that information is not the same. Having one copy of X for
Yeah.
Alice and another copy of X
Right.
for Bob.
Right.
is
Right.
different from having
Right. Yeah.
More questions? All right.
As the
Okay.
power of
Thanks.
Yeah.
I may have to go and pick up my wife somewhere. So
Okay, okay.
Russell, where are you? Yeah. Russell will
Okay.
take you to lunch. I may come
Okay.
back soon, but I'm not exactly sure
Okay.
how long it will take.
Okay.
So I may have to go and pick up Edna. So it will just.
So is this published already, or
No.
Give them
is it publicly available somewhere? Or?
I can send it to you. It's still a bit in progress.
Okay.
Maybe you've noticed.
Okay. I met.
I'll give you the
Oh,
card
great.
and then
Thanks.
I'll be going to. I don't know if everything we're saying is being recorded still.
Oh, right. This is how
But,
politicians get in trouble, right?
Yeah. Anyway, I'll be going to lunch in maybe 5 minutes, if that's okay.
Okay.
So,
problem.
you know.
Yeah. Yeah. Yeah.
Yeah, I saw for two party.
Yeah, when I show